So far, we have understood in detail about ANOVA, analysis of variance, and what is F test, and some basics about the F statistic. So now what we are gonna do, we're gonna put bits and pieces together, and we will pose some questions onto the F test so that we can have a 360 degrees of understanding with respect to the F statistic or F test. So the first question I'm gonna shoot is, which test statistic does it use? The F test uses the F statistic as the test statistic. So how do we calculate that? So F statistic is equals to mean squares between divided by mean squares within. So how do we calculate the mean square between? So mean square between is equal to sum of squares between divided by df between, degrees of freedom between. So how do we calculate the degrees of freedom between? So df between, so between the categories inside a variable. If you have a variable has a 10 categories, then we have to find out the degrees of freedom between these categories. So df between is k minus 1. Okay, and similarly we can calculate the ms within, which is equal to sum of squares within divided by degrees of freedom within. So degrees of freedom within here is nothing but it's within the category. If you have a variable and the variable consists of 10 categories, now each category inside the variance, that's what we are talking about, inside the so that degrees of freedom within. So df within is equal to n minus k. So k is number of categories or groups, and n is total number of observations. Okay, so that's what is the test statistic we're going to use. Okay, what's my next question? So which distribution does it use? The F test uses the F distribution, also known as Fisher's F distribution, to determine the probability of obtaining the observed F statistic. And this is how our F distribution looks like. So let me try to simulate this. Yes, you see that? Now this is what my F distribution. So numerator degrees of freedom and denominator degrees of freedom. So what is our numerator? Our it's mean square between, it's between the categories and then within the category, between the category and within the category. So now what I'm gonna do, so let me put, I will take up initially 4 categories. I have in my variable 4 categories, so 4 minus 1, so 3 is my degrees of freedom. And inside that, if I have observations of 40, let me take the 40, and this is how it looks. So this is the F distribution that I get when my numerator degrees of freedom, that is between, is 3 and within is 40. So if I have 6 categories, 6 categories, then my degrees of freedom would be 5 on numerator, and below let me bring it to 100, and it's getting closer to normal distribution, but still it's a skewed one. If I keep on increasing, of course what we are doing is a right tail test. When I shift, so right tail test and probability value, so p value is 0.05, that's what my critical value, and at critical value my f value is 2.305. This is for the comparison purpose that we can do it when we take up an example. That's not an issue. So okay, so let me keep this one, let me increase the number of observations, let me increase it to 150, and it's getting closer. So here if I increase the categories to 10, and if I make it 100, and this is your fantastically normally distributed curve. So that's what I always say, most of the natural phenomena can be captured and explained through normal distribution curve or your Poisson's or binomial. Other than that, if you want to use any other plot like F distribution or maybe students T or chi-square, these are all fundamentally these are all fundamentally a normal distribution curve with a with the various degrees of freedom. That's it, with various applications. So if you see your chi-square distribution, if you increase the degrees of freedom continuously for certain extent, what you get at the end, maybe after 90 or 91, what you get is your normal distribution. And same thing happens with the chi-square, and same thing happens with the student's T distribution. So that's the reason the most fundamental distributions are normal, binomial, and Poissons, and the derived ones are chi-square, F distribution, and your students T. And these derived ones, students T, chi-square, and F distribution, are very useful for a data scientist when it comes to the feature selection. I hope you got the F distribution. Let's get back to the work. So this is what the uh, distribution that F statistic or F test is going to use in their process. And the third question that I have here is which type of level of measurement or variables this test is applicable to. So this F test is applicable to continuous numerical variables and is commonly used in feature selection and machine learning. Feature selection in machine learning when comparing the variability of multiple groups or models. So let's take a few simple examples. Let's take a house prediction. House prediction. So in house prediction, when you say house prediction, what would be your target variable? So your target variable would be a sale price of a house, correct? So our target variable is sale price of a house. Now predictor variables could be number of bedrooms, which is a categorical variable, square footage, which is continuous, let's keep it aside, location, and age of the house, and number of bathrooms. Now let's take number of bedrooms and number of bathrooms. These are all categorical variable. When I want to know the statistically significant, whether their relation is statistically significant or not between the sale price of a house and number of bedrooms, or sale price of a house and number of bathrooms. So if I want to know the statistical significance of their relation, I need to go for the F test. So using the F test, you can assess the significance of a number of bedrooms in relation to the sale price and select the most relevant features for predicting the house prices, whether number of bedrooms is most or number of bathrooms is most relevant to our sales price of a house. Let's take one more example. The stock market prediction, same thing. Target variable is stock price movement, increases or decreases. So predictor variables would be trading volumes or market indices or news sentiment scores. That's very important. News sentiment scores. So again, you can apply the F test. You can determine the which predictor variables have a significant impact on the stock price movement. And the most important example I just want you to understand is it's a computer vision example, or it's an image recognition. We call it as object recognition. Here, let's take a target variable. It's a presence or absence of a specific object in an image. It's not a complete categorical variable. It's just a binary or dichotomous presence or absence. That's it. A presence or absence. That's our target variable. And predictor variables could be image features extracted from the images such as color histograms, texture descriptors, edge or orientations. These are our image features. These are our predictor variables. When I apply the F test, you can assess the significance of each image feature in relation to the presence or absence of the target object. So this helps in selecting the most discriminative features that contribute to accurate object recognition. So these are the some of the best examples that we can always look after to explain which type of variable we can use which type of variable this test can be applied. Okay, so the next question I'm going to pose here is, which table does it use to calculate the probability? So the F table or F distribution table is used to calculate the probability associated with the F statistic. However, in practice, this calculation is often performed using statistical softwares or libraries. So next, so as we have said libraries, so what all libraries we can use with respect to the Python? So Python libraries that support doing F tests. So the first one is SciPy. The module scipy.stats provides the F underscore one-way function for one-way ANOVA analysis of variance F test. Of course, we are not much bothered about ANOVA one-way test. We are always bothered about two-way test. So stats models, basically this is very important. Stats models, the module stats models provides the ANOVA underscore LM function for conducting ANOVA and F tests together, and this is what is most important for us. And the last question that I have here is, how is this test performed? So first step, as usual, as we have done it for other tests, the first step is to formulate the null hypothesis H sub 0 and alternative hypothesis, which is H sub A, based on the research question. The null hypothesis is often states that there is no significant difference between groups or models being compared. Then step 2 is to collect the data from the groups or models being compared. And step 3, calculate the F statistic based on the variability between the groups. Explained variance we call it as, and within the groups we call it as an unexplained variance. And next we will move on to determining the degrees of freedom for both the numerator and denominator of the F distribution. Then finally, compare the calculated F statistic with the critical F value from the F table or use a statistical software to obtain the P value. So let's take this example. Let's try to demonstrate here. So we have taken the level of significance is 0.05. That too, I'm going with the right tail first. So in that case, my critical F value is 1.345. This, by and large, the concept remains same from z-test or t-test or f-test or chi-square test. The only thing that changes is that degrees of freedom will be added for the t-test, and you will have degrees of freedom which calculated in m plus n minus 1, m plus n minus 2 for the chi-square test. But when it comes to f-test, it's completely different. Here you will have a 2 degrees of freedom to handle the things, because that's how it works. So that's the reason the process remains same. When you have a level of significance 0.05, what you get is a critical value. Here it's F, so critical F value will get, it's 1.345, which is on a right tail. If I move to left tail, your critical value will become 0.736. Okay, so let me change this first. Okay, let me bring it down to the maybe 50, and okay, let me keep that maybe 5,000 each data. We have huge amount of data, but the categories, let me check it for 6. That's enough. Yeah, this is what my data set. Fantastic. So when it is a right tail and 2.144 is my, with respect to this graph, because the numerator, the df's, the degrees of freedoms, df between and df within has been changed. So that's the reason your F statistic, F critical value, critical F has been changed with respect to the 0.05 significance level. Now, but let's take an example. Imagine we got an F value of 1.101. So it falls somewhere here. So in that case, this is my rejection region, and 1.101 is here. So I can my level of my F statistic is not falling in the rejection region, so I failed to reject. And if I change to left tail and my F critical value has become 0.27 for the same DF between and DF within, same if my F statistic, observed F statistic falls at 1.101, again it's not falling in the rejection region, then I fail to reject the null hypothesis. So that's how it works. And if I want to change the level of significance, let me get back to the right tail first, and let me change to 1% of level of significance, and you see that it's the rejection region has been squeezed and it has come to the rightmost of this, and the F value is 2.893, just 2.893. And if I just increase to 0.1, and this is my rejection region, it has increased. And that's all. Here you'll get the F critical value. Of course, if you use a library, you can directly get it from there, or else you can use some online tools to get that value. So this is our critical value, F critical, and this is the level of significance. And you can just calculate the observed F statistic, and you can just check whether it falls inside the rejection region or outside the rejection region. And that's it. That's how we do it. If you use a library, you can get the probability value or p value with respect to the pre-value of observed F statistic. Okay, and then you can directly compare that observed F statistic, p-value of observed F statistic with the level of significance, which is 0.1 or 0.05. Okay, let's get back to the work. So that's what the fifth step. Then once that's done, if the p-value is less than the predetermined significance level, let's take 0.05, then reject the null hypothesis and conclude that there is a statistically significant difference between the groups or models.